Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hey everybody, it's Physics with Beth and Beth. This is AP Physics 1, of course. We are now in Unit 3, which it contains work, energy, and power, and we are on our first video of energy. Now today I'm just going to go through some terms, some equations, units, and some clues in these word problems, and then I'm going to follow that right up with another video on some concepts that are important to know for multiple choice questions, just for concepts that you need to know to do the problems as well. So we'll have this video on equations and then follow up one with concepts instead of combining them how we usually do, because there's just a lot of info here. All right, now let's just jump right into this and we're going to talk about energy. Energy is the ability to do work. Now I will say this, that sometimes energy for my students has proven to be not difficult problem-wise, but hard to grasp your mind around. It's a little bit more abstract than a lot of our logical, concrete things in physics. When we talk about acceleration, your car speeding up, slowing down, we understand what that means. That's very concrete to us. Energy is a little bit more abstract, but hopefully after these videos, you'll be on top of it and you'll have all the energy needed and all the wisdom needed to finish these problems. Pun intended, by the way. All right, so let's get started. Energy is the ability to do work. Okay, that's a pretty broad definition. You're like, I'm still not getting this. All right, it's really a better way to say it is the ability to exert a force to do work. You've just come from our work unit, well, from Unit 3, but our work portion of that unit, and you know that a parallel force that is parallel to displacement, because you have to know what it's parallel to displacement, times displacement is equal to work. Well, energy is going to be that ability to exert a force, to do work. All right, if that makes it a little bit more clear, I hope. But let's talk about some types of energy. You've been hearing about energy probably since elementary, junior high. There's lots of types of energy. There's light, there's sound, there's electrical, chemical, mechanical, thermal, wind, solar. You could just go on and on. There's lots of geothermal. There's lots of types of energy. All right, so, but we're only going to talk about a few types in this unit 3. Now, we have to step back though before we can dive into this, and we have to talk about the first law of thermodynamics. And you're like, whoa, Beth, I did not sign up for thermodynamics. I am in physics. We can all count our blessings on that. As an engineer who took thermodynamics in college and used some of it in my career, yeah, I prefer to be in physics as well, but we need to talk about this one concept. So let's talk about this. First law of thermodynamics says this. It's really called the conservation of energy law a lot of times, but its energy cannot be created or destroyed. It simply changes form. All right, so here's what that means. Let's use your cell phone. We have it with us all the time. We're always using our cell phone. Let's talk about that. All right, we plug our cell phone into the wall to charge. All right, and that's electrical engineering. Now, where is that energy coming from? That energy is coming from your power plant, and your power plant's probably getting it from many ways. It may be solar, it may be wind, it may be geothermal, or it may be burning coal into steam to then turn a turbine, which is movement, energy of movement, into and turn a turbine that then turns the generator that produces electricity. So there is lots of ways that those power plants are making electricity to then be sent to your house through transformers and all those good stuff, those electrical lines, and then you charge your cell phone. Well, that electrical energy from your charger, from being plugged into the wall from your electricity, is now being turned and converted, transformed, I should say. So it's changing forms into chemical energy in your battery. Once your phone's charged, you start using it. You have light. From the background on your phone, there's light energy that chemical energy is being, again, transformed into. There's sound. There's vibrations is energy of motion, your kinetic energy. It's turning into radio waves to talk to your cell phone, your cell tower, sorry. So all of these different energies, it just keeps changing forms. It never is created or destroyed. Electrical goes to chemical, chemical goes to light, sound, heat. As your phone heats up, you'll feel it heat up, that thermal energy. There are so many types of energy out there, but it's just all changing forms all the time, not created or destroyed. All right, that's what first law of thermodynamics says, and that's going to be extremely important to know, and that's why we only do the first law. It's going to be important to know in our problems when we do those, okay? So remember that. You can't create it or destroy it. In other words, if you're at the start of a problem and you have 700 joules of energy, then at the end of the problem, you still need 700 joules of energy unless work has been done to add energy to the system or friction has occurred to take energy out of the system. But it will not be created or destroyed. It's just going to be added from another form or taken away in another form. Okay, perfect. All right, now we're going to continue on. We have a term, mechanical energy. What is mechanical energy? It's the energy from position and movement in a system. All right, and we're going to give you an equation on that momentarily. The symbol for ME, for mechanical energy, is ME. And by the way, energy, we didn't say, but the units are a kilogram times a meter squared over a second squared. And if you remember from work, we have designated that, the scientist, Mr. Joule, with that honorary unit, just like we did Sir Isaac Newton with the Newton for force. Okay? Now, mechanical energy has three types of energy here that make up mechanical energy. And these are the three that we're going to be using in this unit all the time. All right? The first one is gravitational potential energy. Now, the symbol for that, I know that in your elementary and junior high, you've probably been using PE to designate potential energy. But actually in the engineering physics world and the AP Physics 1 and C world, we don't use PE, we use the symbol U. And U is your potential energy. Now since this is gravitational, we put a subscript little g there. All right, that's indicating your gravitational potential energy. Well, what is that? That's the symbol. All energies are measured in joules. Capital J is how we designate that. All right, and but what does that mean? Well, it's stored energy, because potential energy is just stored energy. That's important to know. But this is stored energy specifically due to your position. And so stored energy due to position. Or really, we're talking about your height, right? So in other words, I have this ball that's shaped like the earth, and if I were to drop it from here, from this height, I would get a pretty good bounce. But if I do work and add potential energy to the system, and how I'm going to do that is I'm going to force this up with the force of a push, and now I'm higher off the ground. I have done work. I have pushed this ball up. There was displacement and there was a force of a push. Now, if I dropped it from up here, it would have a higher bounce. Why is that? Well, it's because it has more gravitational potential energy here than it did down here. So you're going to see that in that higher bounce because it's just going to change energy. It's going to be going from potential energy. When I drop it, it's going to change into kinetic energy. And it's going to have less potential energy as it falls because less height, and it's going to have more kinetic energy. All right, and we'll talk about that a little bit more. But know that I can do positive work and add energy to my system and give it a displacement higher, force of a push, and now we have more gravitational potential energy. All right, the formula for that looks like this. UG equals, and that should be a subscript. That almost looks like you're multiplying by little g. We want to be careful with that. All right, we have a little g here. Equals mgh, where m is mass in kilograms. We all know that we're using kilograms. Little g, we know what that is. That's the scalar version of acceleration due to gravity. That's meters per second squared. And our h is just our height in meters. Now, if we were to multiply all those units together, we would get kilogram times a meter over a second squared times another meter. That'd be kilogram times meter squared over second squared. When your units work out, you're on the right track. All right, so we got that. Now we're going to talk about spring potential energy. All right, spring potential energy is actually that we talked about the spring, that it can do work, and we talked about that has force, that your springs have force. If they're compressed, when you let go, they can produce a force that will push an object. All right, if it's stretched out, like vertically, it can produce a force that can pull the object up and down and bounce up and down. All right, so we have spring potential energy. Because of that force, it can do work, which means that it can have potential energy. So the spring potential energy looks like this. It's still the symbol. Let's keep it constant here. Our symbol is U again, because it's a potential energy, but with an S for spring. Our formula looks like this. US equals 1/2 kx squared, where K, we know from our past force unit with springs, that K is the spring constant. All right, it's a spring constant that has a unit of a Newton divided by a meter. X is the distance stretched or compressed. Stretched or compressed distance. I'm starting to write kind of small, sorry about that. And so I don't run out of room, it's in meters. And so we have a Newton times a meter squared over meter, which is a Newton times a meter, which, go figure, is a joule because it's kilogram times a meter squared over second squared. Again, units work out, we love that. That means we're on the right path. All right, do not forget, I will say this, physics, time is never your friend on a physics test. All right, so it's always easy to drop this half or to drop this square. Don't do that when you're rushing around on your test. Try to be mindful of that, because that's a really easy mistake I've seen students make a lot in the past. All right, and all that is, again, it's stored energy, but it's stored energy due to a spring being compressed or stretched. That's all it is. All right, then we have kinetic energy. Kinetic energy, the symbol, again, we're going to keep constant. This one is what you're probably used to, Ke. And Ke's equation looks like this. Our kinetic energy is 1/2 mv squared, where your mass, m is mass in kilograms, just like it was for potential energy. And your v is our velocity. All right, and it's in meters per second. And you square that, you have a meter squared over second squared times a kilogram, and guess what? We're back up to here, we have a joule, again, it works out, yay. All right, so those are your three formulas for potential energy due to gravitational, or gravitational potential energy, I should say, the spring potential energy, and your kinetic energy. Now, here's some clues that you're going to need. And by the way, mechanical energy, let's go back up here and get this. Mechanical energy just equals the potential energy due to gravity, the potential energy due to the spring, and the kinetic energy. When you add all three of those up, you get your total mechanical energy. Now, some clues you need to think about. Height is in this equation. If you are on the ground and your height is 0, you have no potential energy. All right, so you wouldn't have potential energy when you're looking at your total mechanical energy, trying to add that up if you were on the ground. If you don't have a spring, then you have no spring constant, you have no spring that's been stretched or compressed, so there's no spring potential energy. All right, if you are not moving, you have no kinetic energy. You must be moving and have some velocity, or you have no kinetic energy. So those are clues you're going to look for. If you're moving, you know you have kinetic energy. If you are at any height off the ground, you know you have potential energy, gravitational potential energy. If you have a spring in your problem, then you know you have spring potential energy. So those are going to be important to know. We also should have mentioned that the kinetic energy definition is this is energy of movement, or it's energy let's put of movement, or yeah, that's good. We can leave it at that. But it's because you are moving, you have kinetic energy, okay? Potential stored and energy, we call it energy of motion, really is probably the better way of putting that, energy of motion, but energy of movement's fine. Okay, perfect. That is your basic definitions with some equations, as well as some tips on remembering what kind of energy do I have. It's going to be different in every problem, and you're going to really need to look for height. You're going to need to look for a spring, or you're going to need to look for movement. Simple. One more thing I would like to add before we sign off here is that thermal energy, because we're going to be talking about thermal energy because that's going to be from friction. Friction is going to create thermal energy, heat energy, that is going to take energy out of your system. All right, and thermal energy has an equation that looks like this. First of all, this is the symbol, just to stay consistent, so we always have that. That's the symbol, and the equation is that thermal energy is going to equal that friction times our displacement. And that's going to give you your energy. Okay, it's also the work that friction does. If you see that, the force times displacement, but we're getting into that in 2 more videos, that work energy theorem. Okay, all right, perfect. Thank you for watching. I hope this helps. Hey, listen, if you like these videos, we would love to see those likes so that we know that they're helping and that you all are enjoying them, and you want us to do more of them. And also, if you want to keep up with our videos, then just subscribe, hit that subscribe button, and we'd love for you to get notifications then on when we're posting new videos. And thank you for watching, and happy physicsing.